Now, whilst flat earthers can't agree on a complete flat earth model,
there is no such thing as the one and only complete model for all of Earth/existence and all that we experience here. Different models are required to explain different things. They are only tools. Different models can be used to explain a single phenomenon. All could theoretically work on paper, but that doesn't mean any or all of them would be true in real life or would be without flaws. The globe, for instance, uses a wide variety of different models in attempts to explain different phenomena that we observe. Sometimes globe proponents are forced to create a specific model or models that requires them to draw something that is physically impossible to replicate in reality. One example is that of eclipse shadows. Conical shadows that taper off to a point do not happen like this in real life. This is an impossible shadow that cannot be replicated with a physical model, yet this is what the globe model demands for it to work.
There are so many anomalies in eclipses. You can study the shadow using real-life scale model. I've tried with Pupung. We're using real sunlight, no question about brightness, lumens, and so on. But don't do it in open air, cause the bigger the light, the smaller the shadow. In total solar eclipses, the source of light should be the same with the object that eclipses it. Using scale model, for a 10 centimeters Earth, you have to use a 2.92 meters of pipe. This is very important to make the source of light to scale. The result is quite devastating. The shadow is about 16 times bigger than it should be. In reality, eclipse shadow size is about 70 miles or around 100 kilometers. They make it in CGI cartoons as if a 3,474 kilometers of moon from 384,000 kilometers distance can make a 100 kilometers of shadow. So they make CGI cartoons with shadow shape like a pencil. It doesn't exist in reality. With real-life scale model, the shadow is actually 1,000 miles or 1,600 kilometers. With the globe model, eclipse shadow would cover the whole Kalimantan island. Unbelievable! With the globe model to scale, eclipse shadow would be so big that can cover Portugal, Spain, and France at once. This is a disaster for the globe model. All your life, you only see eclipses of fantasy. On the other hand, in the flat earth model, the diameters of the sun, the moon, or whatever object eclipsing the sun is about 32 miles or around 60 kilometers. If you don't like mathematics, you can use AutoCAD, a neutral software for professionals. You can verify by yourself from 5,000 kilometer height. They will make shadow size exactly like reality. 105.7 kilometers like the real eclipse shadow in Idaho Falls.
There are many more issues with globe models, but neither the globe nor flat earth has just a single, complete model for literally everything, all at once. To expect one or to bring up the point as if it is relevant is ridiculous and certainly isn't required to prove the overall shape of the ground you walk on and the water you sail upon, but let's continue.
Now, whilst flat earthers can't agree on a complete flat earth model, they do seem to have a general consensus that the earth is a flat plane and that the sun and moon circle above it whilst maintaining a fairly constant altitude. Although they can't agree on what that altitude is.
That is because the distance to any celestial object cannot actually be proven or verified, only assumed. Whether one is using triangulation, parallax, redshift observations or radar. Assumptions and several other issues lie at the core of any distance claim to the sun, moon or stars, as flat earthers have pointed out many times before. Remember that refraction is always present as well when observing anything through several layers of atmosphere. We always see an apparent sun, not the actual due to this refraction. No physical measurement to the sun will ever exist.
The distance from the North Pole to the South Pole is about 11,800 miles. which would put a flat Earth at around 23,500 miles across. Now, if the sun and moon were hundreds of thousands of miles high, then they should be visible high in the sky 24/7, which obviously they aren't. Which sort of forces the claim that they are in fact much closer to the Earth, with general distances given of only around a few thousand miles. Even around 3,000 miles high though, the sun should never set. If the sun were above one edge of the flat Earth and you were at the other, 23,000 miles away, the sun should still be 7.5 degrees above the horizon.
Dave, you are using an orthographic projection here, so of course it won't set in that view, regardless of any claimed altitude. The use of orthographic side views is a common tactic of globe defenders. You need to use a first-person perspective view here, as that is how we see the world in real life. As been shown countless times, perspective view along with atmospheric refraction creates sunsets on a flat Earth.
With 3D software, you can model the atmosphere very accurately using refraction settings. We're not talking about drawing it and making it visible, we're talking about drawing the layers with their real effects on sunlight.
We actually took some real sunset videos and compared them with both the flat Earth model and the globe Earth model. And guess what? If you play the 3 videos at the same time, you would not know where the flat Earth model is, because it really looks like real live videos.
Many scientists think that the flat Earth model can't work because it can't represent sunrise and sunset. What are they going to say after studying this proof? Is it going to make sense to some of them now? They can't ignore the atmosphere, and all we did to make the flat Earth model work was add the atmosphere exactly how science represents it.
Here we have our 2 horizontal planes with a perspective grid over it. You can see the trees rise up toward the horizon and get smaller in size, and the clouds appear to get lower in the sky as they appear to converge into the vanishing point. The clouds seem to drop toward the ground in the distance, yet we know that the clouds are still thousands of feet above the Earth's surface. The same thing with the sun. It is always high above the Earth's surface, but seems to touch the ground as it reaches a distance outside the limits of our optics. As the sun moves farther away, the horizontal planes will appear to merge. So here, we have our observer on the left looking off as far as he can see. When you, as an observer, stand looking as far as you can see toward the horizon, the sky plane and the plane of the ground you stand on appear to converge at the end of your eyesight in the distance at the vanishing point.
So continuing on with the differential rate of information loss, you can see the effect here with these bottles. The horizon is set by the observer height. So as an example, if you can see 9 feet at a 3-inch elevation above the table, and you lower your height 33% to 2 inches, their lower horizon is now closer by 33% and is now at 6 feet. And this represents the new lower horizon line. The rate of descent along the tops of the bottles is greater than the rate of ascent along the bottom. The compression rate is higher along the bottom, and the angles are more open along the top. Again, we have compressed angles along the bottom, which correspondingly increase or expand the angles that we're looking at the tops with. Things will appear to descend above our eye line at a faster rate than things ascending below. So you can see the yellow line descending now at a faster rate than the ascending rate of the blue line below. Therefore, things below our eye line will appear somewhat stable in relation. In other words, it will appear like a bit more of a dramatic decrease in size or in height for the objects on top, whereas the bottom will appear somewhat stable even though the angles are more compressed. As we'll see, if information continually moves into a narrower and narrower angle, eventually the lower part of the bottle will be unresolved while the top still remains. If I were to extend these bottles along a very long table, the bottom would disappear first with a lowered observer height, yet the top would remain. If I extend the table even further, the entire bottle will vanish when the top of the bottle descends below the lower horizon line. So as an example, a bottle on the street was filmed 107 feet away at different heights. When the camera is lowered, the bottom is cut off. the bottom compressed until the information vanished. With a higher viewing angle, the object comes back into view in entirety. When lowering or raising your iPhone, which has a small aperture in comparison to, say, your eye or a high-end camera, to view a flashlight on a very long floor like a supermarket, the flashlight, if it's low to the floor, disappears due to a limited viewing angle. So again, you can have your phone with the camera side down along the floor and very close to the floor, and you can do the same with a distant light source or any object for that matter, and you can raise and lower either your phone or the light source, and you will not be able to see it when both are on the ground at the same time. So raising the flashlight carries the same implications as lowering your eye height. The light is shining parallel to your position. Keep that in mind. That light is shining essentially in a direct line straight to the or what you would think would be a direct line straight to the phone, but the phone camera cannot pick it up. It cannot resolve the light. It has hit its angular resolution limit. So on the left side picture, you can see that the light is about 8 inches off the floor and it's visible. On the right, the light is lowered and placed on the ground, and it's about 1 centimeter up, and it disappears. In essence, it is set below the eye line of the observer, which is the camera, within the diffraction limit, almost like a mini sun.
When inland, there are many features on the Earth's surface that create an artificial horizon. For example, if you live in a valley, the sun will set behind the mountain and disappear from view much faster than if you live in an area with no hills or mountains or next to a large body of water. Where I live, there are many trees surrounding me, so the sun disappears behind them long before the daylight fades, and since we are told almost from birth that the sun is going on the other side of the ball, most just accept it and don't ever give it a second thought. The next thing that causes the sun to set and rise is our atmosphere, or atmoplane, as I like to call it, since we live on a plane, not a sphere. Think about the ocean. There are many layers of visibility. First, you have the sunlight zone, which is the top layer we are in the most, and it's still easy to see in the water while the sun is overhead. Then you have the twilight zone, and the light is now less able to penetrate the water. After that, you have the midnight zone, where it is too dark to see even at high noon because the light can no longer go through the layers of water. The same thing is happening on our Earth's surface, but at a much larger scale. Clouds and water vapor obstruct the light of the sun, and it can no longer illuminate your area. This is a clip from a video made by my good friends Zach and Steve. In this animation, Steve rendered the stars over a flat Earth. The top is rendered with the atmoplane, and the bottom is rendered without, showing how perspective alone does not explain how the luminaries appear to go below the horizon. The water vapor in the air acts like a lens. This is called atmospheric lensing in mainstream science and is explained here.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes.
So not only does the water eventually obstruct the light, but all the billions of tiny water droplets behave like a lens. You can emulate this with a lens and a light source like I do here. This candle will take the place of the sun. Watch as I slowly move it back in a straight line, and also it stays at the same height since I have it placed on this mason jar. The atmoplane and your vision create what we call a personal atmoplanic dome, or personal atmospheric dome if you please, which is the shape of the lens dictated by our eyesight. This simulator, ironically made by a globe Earth believer, shows how this works. It's not perfect, but it certainly is close. This can give you a better idea of how the sun can set visually without having to go behind an imaginary curve. Okay, I want to go back to my sunrise video and take a look at how light reflects off of a flat surface. I went to this online tool that lets you create different simulations of a light source and a reflective surface, and this is simulating the sun over flat water. The light is radiating from the center of the source out in all directions. Look at how the light rays bounce off the reflective surface and off to the distance at an acute angle. So here's our observer again, and you can see the reflected ray reaches our observer before the source does. This is what creates the effect we see at sunrise or sunset. The first thing we see is the reflection of the sun, not the actual sun. The light of the reflection is closer to us, so we see that before we see the sun itself. Watch in this video how the sun's reflection begins to come into view, and it's not round, it's squashed, because it's reflecting at a sharp angle. There's a line here where the angle of the view is so sharp, the water becomes a mirror and it's reflecting the sky. So when the sun approaches you and gets close enough for your eye to see it, the disk appears to rise up from the reflection because visually, it is now within the limits of your eyesight. As the sun moves closer, you see the reflection remain below the disk for a short time, and then it's gone. This can only happen on a flat surface. Here is an example on a smaller scale. Watch as this little ship comes between the observer and the big ship, showing you how the reflection is closer to you than the object itself. And that is how the sun sets and rises on a flat Earth.
The other big problem, though, is what their angular sizes should be doing. When we view an object, we see an angular size, which is the angle across the object that we see based on its physical size in relation to its distance away. The physical size of the object won't change, but as we change the distance, then the angular size is directly affected. So if we have an object that is 5 degrees wide when it's 10 meters away, and we double the distance to 20 meters, then the angular size will halve to 2.5 degrees. If you're in Egypt when the sun is at high noon, it would be 3,000 miles away from you straight up and has an angular size of half a degree. 6 hours later, when we see it set, it's now 7,000 miles away across the Earth's surface, meaning the sun would then be 7,600 miles away from you, which is 2.5 times further than it was at noon, and so it should appear to be only 1/5 of a degree in angular size.
For the information above my eye line, the descent rate is now steeper, just like with the bottles, but I have less of an angular compression rate, right? The angles are more open. So these angle pairs, the 8s or the 1s or the 11s, etc., must always remain in proportion, but diminish together according to the ceiling or floor distance. If one angle decreases, the other increases, but they are both diminishing with distance. Theta is never met along the top, again, because the horizon distance is set by the bottom. It occupies 50% of my vision, so wherever the information above my eye line is at that point, when these two halves collapse, is what I see above my eye line in my perspective. The top continues on independently, but you will never see the objects diminish in size and reach theta along the top because they will have already set into your lower horizon.
What their angular sizes should be doing.
They are gone to your vision. Note also the steeper descent rate at the top. The higher the ceiling, the steeper the descent rate within our perspective. This is how our brain interprets it. The nearest ceiling or floor sets our horizon. Similarly, the nearest wall would set the vertical vanishing line if we were up against a long wall, let's say. So if we collapse our diagram here and we press the image downward and along the top and upward along the bottom to reach a essentially horizontal line. So you see that along the bottom, the angle 8 doesn't have to travel very far to get to the purple line. but the angle 8 above has to travel quite a bit more to do that. But essentially what you're left with is basically what we see in perspective as I've depicted here in the upper right. You have the larger angles, resolution angles along the top, and a steeper descent rate characterized by the orthogonal lines. And along the bottom you have more compressed angles and those closer transversal lines, and more stabilized or shallower orthogonal lines. You also have the object larger to start out with, but then gets rapidly smaller with distance because of the how close in proximity those transversal lines are. And along the top you have the object start out smaller, but it remains relatively stable because the angular size compression rate is not as great, so the angles remain somewhat large as it descends away from you, and it maintains its relative size for the most part. And at the end it will eventually set into the horizon. So as you probably have guessed, the sun is a practical example of this. The sun and moon set because they travel a short distance in a straight line along the very high upper boundary. If we extend our ceiling to a tremendous height, you see that the rate of differential angular compression between the floor and the apparent ceiling is large, and the descent rate steepens dramatically. So the object descends to the vanishing line rather quickly while maintaining a relatively constant resolution angle as it travels. It therefore does not experience an appreciable change in size. Once it hits the lower horizon, it sets. Again, this occurs without the object having to travel very far because it is so high up, and without an appreciable change in size. Stated another way, the higher something is, the less it changes in appearance. The distance it has to travel before it sets is dictated by how far we are seeing below the eye line, which is in most cases about 3 miles. This is for a diffraction limited system, but remember there are aberrations and refraction effects within the atmosphere that can alter the size of objects and distort them.
Both the sun and moon's angular size remain constant from one horizon right overhead and to the opposite horizon.
And then of course there's this video right here, which apparently was shot in the desert where there's going to be a lot less moisture, and so whenever there's less moisture you're going to obviously have less refraction and magnification.
You don't get to pick the anomalies that seem to agree with your views and ignore the common observations that don't, and still call yourself an honest investigator. That is intellectually dishonest.
And that's the brand name and make of the solar telescope. Now it doesn't have any zoom on it either. It's locked in at 500 millimeters. And we have shrinkage over here from the noon picture, and a little shrinkage over here. And as you can see, it's bigger. So as you can see on this day, the sun did actually change sizes throughout the day. And as you can see, it's starting to shrink back down again. And it isn't quite as big as the November picture, but bigger than the 4th of July. Does the sun change sizes throughout the season? Yes. Does it change sizes throughout the day? Yes, it does.
One horizon right overhead and to the opposite horizon.
Back to the Copernican principle, and this is what they tell us. The sun is 93 million miles away. Now I'm going to show you evidence through sunsets that shows the sun light following the sun over the horizon, and it shrinks as it goes over. Now there's no way it would do that if the sun is 93 million miles away. Okay, first I'm going to show you some footage from the ISS. Okay, now watch this animation. Watch this sunset. Now this is exactly, if they came to me and said do an animation, this is how I would do it if the sun were 93 million miles away. Just like that. Have the whole horizon fade evenly.
One horizon right overhead and to the opposite horizon.
But that's not what we see. Okay, wow, look at that. Look how the light lifts off the ground like a big wedge or like lifting up a sheet of paper. That's incredible footage. Okay, here's a little illustrator or a little cartoon from a website called timeanddate.com. It's really funny that they would have a perfect illustration of a sun rising and setting on a flat earth due to perspective. Okay, these next 3 slides, the sun is almost set already behind the horizon, but watch as the sunlight shrinks and follows the sun. It's definitely a locally illuminating sun, not far away, not very big, and definitely not 93 million miles away. Okay, remember this video from the beginning of the video? I showed you this one and how it's circling over the earth, and watch it sweep to the right like a bowler bowling it in there for a strike. Okay, now I want you to pay attention to the way the light follows the sun. The sunlight's going to shrink, right, as it follows the locally illuminating sun.
One horizon right overhead and to the opposite horizon.
Watch this. See it shrinking, following the sun? You do not get that if the sun is 93 million miles away. The entire horizon should fade evenly, just like this supposed shot taken from space of the Earth. You can clearly see the way they depict it. They depict the demarcation between day and night, or light and dark, as a long straight line. And you can see the long straight line moving as one solid piece. That means that the sunset should all fade, the entire horizon should fade evenly. But that's not what we observe, as we will see and as we've seen in the footage so far. The sunlight shrinks and follows the sun over the horizon. So these time-lapse sunsets are definitely the nail in the coffin for heliocentrism. But this particular one here, shot from above the clouds from this observatory, is the final nail in the coffin. Look at how the sun just shrinks and the light shrinks to nothing. That cannot happen, as I showed you in the when the sun illuminates the entire Earth, which it does from 93 million miles away. It has to. You don't get this isolated look at the sunlight trailing the sun. That's only possible with a small sun, close, not very high, illuminating locally. I mean, if this isn't proof to you, then you gotta take the blinders off.
what their angular sizes should be doing.
The home point has been up. Takeoff.
.444, so we have about a minute left. If you all are just joining us, this is flat Earth sunset. As you can see, the sun is pretty much out of our line of sight right now due to perspective. As you can see, it's getting smaller and smaller as it goes further and further away, not down. And we're pretty much down to the last minute here of the sunset. And as you can see, it's just a tiny little speck, and it's gone. It's gone.
Now, flat earthers have put this down to atmospheric magnification, claiming the Earth's atmosphere is magnifying objects more and more as they get further and further away, which causes them to always appear the same size.
And we have shrinkage over here from the noon picture.
The first obvious problem with this, though, is why is it only happening to celestial objects? Why don't planes, birds, balloons, and everything else in the sky also stay the same size as they get further away?
How much have you tested that claim, Dave? First off, the sun's light is traveling through much more air and water vapor than objects that are much closer to you, such as planes, birds and balloons. Celestial objects have to travel through more mediums and distance/thickness of those mediums, especially at the horizon. Varying distances and atmospheric conditions in an area will give you different results, to where you'll either see shrinking, maintaining size or appearing larger than normal.
Why is it only happening to celestial objects?
I snapped this picture of the Willis Tower. And this is, if you go on Google Earth, this is right about the area right here where I believe I was when I took that picture. Looking across, it's only about 0.6 of a mile. So I'm just a little over a half mile away, and look at the size of the tower as compared to the car that was diagonally in front of me. We were looking at the Willis Tower from this direction right here when we were on the other side of the lake. Now, okay, so let me slide the car over and shrink it down to the appropriate scale beside the boat. Do you see something rather interesting here? This building is significantly magnified. The image on the left shows the size and scale of the building next to a car at 0.6 of a mile away. The image on the right shows the same building and the same car with a boat at 46 miles away. The atmosphere really is acting like a lens.
Why don't planes, birds, balloons, and everything else in the sky also stay the same size as they get further away?
Both these images were shot from the harbor area here. The red line at the top is where we were in the boat. We're just about to depart when I asked Tony to stop, and I got the camera out to shoot Chicago. And the lower red line is where we were on the beach when I took the picture on the bottom there. So, and the distance between those two locations is less than a quarter of a mile. So it's negligible. We're still looking about 46 miles across either way. Now, here's the shot from the beach before I zoomed in. Now I'm zooming in, zooming in, zooming in, And I'm going to stop it right about here. That's about halfway on the zoom, and I believe that's where Rick had the camera set when he took the picture above. Based on the size of the building right here, I'm going to guess that he was about halfway. Alright, so let's go ahead and continue the zoom. And this is zoomed all the way in. The Nikon Coolpix P900 has an 83 power optical zoom, and that little punch in after that was the digital zoom afterward. It has a digital zoom that goes beyond the 83 power. I did not go all the way in with that. I just punched it a little bit because I wanted to frame it with the ship right there. So that's 83 power plus. So gonna guess it's probably the equivalent of about maybe 90 power zoom or so right here. Now let's bring the picture in from the halfway zoom, and I'm going to go ahead and bring our car back in and slide the picture in from Chicago, and I'm going to scale the car to the appropriate size to the boat right here and go ahead and slide the car over to the building. So this is what the car and the building look like at half zoom. So let's try something else here. I'm going to unfreeze the video and back it off so it goes backwards, and we're zooming out back to the shoreline. And now I'm going to bring it forward again, and let's see, right about here is where we have some fairly decent resolution where you can still make out the building. I'm going to zoom in here with the computer. This is a computer zoom now on this still image, and I'm going to bring the other image in from the half zoom and scale the car over to the digitally zoomed in image of the almost completely zoomed out shot. And so you got three different zooms here. One almost completely zoomed out, one zoomed about halfway on an 83 power optical zoom lens, and the one on the right, of course, all the way zoomed in with a little touch of digital zoom on top of that in the camera. And when looking at these images compared to the one on the left, which is just shot with my iPhone, I gotta tell you, it looks like it's being magnified to me, especially when you consider the fact that that building is like 45 miles away from that boat. It's 45 miles away. So it looks like there's some serious magnification going on here. And, you know, some of that could be due to the lens, I'll give you that. But I also know what I could see with my own eyes. Now, I understand you may not want to take my word for it, so all I can say is go up there and do it yourself. But based on what I saw with my own eyes, as well as what the quote-unquote experts had to say regarding how the atmosphere can act like a magnifying glass, I'm still going to go with it as being magnified.
Science is the same of that of a lens. Here's a simple example. So the atmosphere really is like acting like a lens.
Yes.
A bigger and less obvious problem, though, that I think exists is the problem of the shape of the atmosphere that would be required to magnify objects to such an extent. But since we're about to talk about the shape of atmosphere, it seems like an appropriate time to tell you about today's sponsor, Squarespace.
Squarespace is one of the leading website creating and hosting services on the market. They have dozens of website templates to choose from that suit all needs, and the templates can then be extensively customized very easily to make your website look however you want. But Squarespace offers many more tools as well. You can set up a blog, you can add a scheduling system to allow appointment bookings, you can set up your own online store, or even start a marketing email campaign for your subscribers. To start with a free trial today, head on over using the link in the description, squarespace.com/Dave McKeegan, and to get 10% off your first purchase, then use the code Dave McKeegan at checkout.
Now, back to the video. When an object's angular size reduces as it gets further away, the angle with which the light from it is entering our eyes is decreasing. So when we magnify an object and we're increasing the angular size that it appears to us, we must be increasing the angle that the light is entering our eyes, which is done via refraction. This is where light travels through mediums of different densities, and as it moves between them, the change in density will cause the light to bend. Now, how much it bends depends on multiple factors, such as the difference in densities between the mediums and the angle with which the light is traveling relative to the mediums. Now, we can't change the incoming angle of light from a subject that's traveling towards us, which means we have to vary the angle of the medium, which in the case of things like a magnifying glass or a camera lens, is glass. If we shine light through a flat piece of glass, it will bend when entering the glass because it's moving into a higher density medium, but it will bend back by the same amount when it exits the glass. So the angle that the light is traveling remains the same, although its position has changed slightly. Hence, when we look out of a window, nothing gets magnified. However, if we look through a window at a very tight angle and then we open the window, the position of objects will seem to move slightly, but their sizes will remain exactly the same. For us to magnify something using refraction through glass requires the glass to be curved so that the light entering from either side will be focused inwards towards the eye. This creates the appearance of a greater angular size, which is why magnifying glasses always use curved glass. Magnifying glasses always use curved glass.
And one of the things that's really nice about these are magnifiers that are flat and the size of a credit card, so you can put them right in your wallet. Slide that sucker in there and then have a magnifier with you. Now, if you wear reading glasses or suffer from farsightedness or just need to be able to read things on the road, it's not always convenient to have a pair of reading glasses. You might not have them when you need them, and this will allow you to see really small things, read fine print. I want to show you how they work. Alright, so here's the pack of Fresnel lenses. What I will say about it is you get a bunch of them, so you can put them in all your wallets. But it's the size of a credit card, and it's just a little piece of plastic. You can see it's very flexible. But the way a Fresnel lens works, as I understand it, is it basically kind of dices up a magnifying glass. So if you have a magnifying glass, this kind of really heavily curved glass, you might even see on lighthouses how they have like a ball of glass up in the lighthouse, and that helps project out the light. It's kind of the same thing. But instead of having this big bulbous piece of glass, what you really need are those angles on the edge of the curve. And so what a Fresnel lens is, it's like taking a magnifying glass and cutting it in really thin layers, and then just taking that curved edge of the glass and then stacking those curved edges of the glass on top of each other to create a magnifying glass that has a lot of different layers with different angles to create the magnifying effect, but in a really flat surface.
And then by using the nail head, carry drops of water to it and plonk them on. There we are, that's a rounded bead of water. You can probably just see it sitting there in the loop. Just take a little bit off my finger, and that takes it back a bit. Ah, that's perfect. It trembles a little, but it really does work as a magnifying glass.
And crucially, the glass has to be convexed in order to direct the light inwards towards the observer. If it's concaved, it will cause the light to disperse outwards and objects would then appear smaller. And this is where the shape of the flat Earth atmosphere becomes a problem. Because we know that air density reduces with altitude and the drop is proportional to the rise in altitude.
I'm actually...
But if the Earth were a flat plane, then the changes in density of air are also flat, which, yes, would cause slight shifts in the positions of objects when they're at very low angles, but would have absolutely no effect on the angular size of an object because all of the light is being refracted by the same amount.
You sure about that? You sure about that? That's why?
To have any chance of magnifying an object with the atmosphere would have to have a convex curve to it. But we know the air pressure gradient is proportional to the altitude above sea level.
Actually,
Which means the sea level would also have to have a convex curve to it as well.
Which means the sea level would also have to have a convex curve to it as well.
No, Dave. It is not the overall shape of the atmosphere nor the ground, but it is the shape of what is in the atmosphere. Countless, curved drops of water stacking upon each other, both physically and perspectively when looking out at the horizon. Note we are looking through more water vapor when looking straight ahead than you would looking straight up at the sky. The water droplets alone creates a flat Earth flat atmosphere magnifier that varies due to conditions. The Earth does not have to be curved to magnify objects at the horizon. That is a ridiculous notion.
So the atmosphere really is like acting like a lens.
Yes.
And, science is all about testable, observable, and repeatable data, right? So to alleviate the problem of distorting the edges because the magnifying glass ring is too small, I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here,
The atmosphere really is like acting like a lens.
yes.
Atmosphere really is acting like a lens, and this is how much of the city is missing due to the lensing effect, the magnification of the atmosphere. You're missing, a good portion of the city just by pulling my iPhone back on a 3-foot long desk. That's how much I lost of the city. And as with any scientific experiment, you always try to improve upon what you did before. So I got some foam core, made a little housing for the magnifying sheet, and pasted the city on the back there, and I made it as 2 separate pieces so that I could flex it as necessary, because I think that there are different types of atmospheric conditions that would allow for more magnification versus less magnification. So in this scenario, you have more magnification, and in this one you have less. And for this one I decided to put the Toronto skyline into my little box here. And let's try it again. Okay, we're all the way up against the glass. Now let's zoom across the lake. And wow, look at that. The lower portions start to disappear. Now let's zoom back in to get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever.
That's all before you factor in problems like that to create a 2 to 3 times magnification requires refraction levels far more drastic than atmospheric pressure gradients would allow.
According to who and based off of what information? You just threw that claim in there without backing it up. Again, magnification levels will vary depending on conditions. A building at a few dozen miles away can become magnified several times larger. As was shown, the sun will sometimes shrink and sometimes maintain size. The sun shrinking at sunset cannot ever happen in the globe model. Observations only fit flat Earth.
Media actually defines atmospheric refraction as the deviation of light or other electromagnetic waves from a straight line as it passes through the atmosphere due to the variation in air density as a function of altitude. So it's saying as the air gets closer to the ground, it's more dense. So atmospheric refraction near the ground produces mirages and can make distant objects appear to shimmer or ripple and appear elevated or lowered, stretched or shortened with no mirage involved. So now let's take a look at the sun. Is this not what we see? Can we not see ripples in the setting or rising sun? I think we are clearly seeing atmospheric refraction here. Could we also conclude then that due to this light refraction the sun appears to be lower than it actually is, as previously stated? Now, people will argue that the flat Earth theory must be wrong because if the sun were circling overhead, then it must get smaller and smaller until it ultimately disappears. This is essentially what happens though. But as the sun approaches this vanishing point, the light begins to distort and refract, making it appear to sink below the horizon. In some parts of the Earth, though, this refraction does not take place. Couldn't the phenomenon of the sun turning distorted and rippled, appearing to sink and changing darker color, happen on a globe too? I mean, after all, we are rotating away from the sun, which increases the distance the light is traveling to us, right? That can account for the light refraction, right? On a globe Earth then, you would need to justify that the sun is not actually moving further away from the observer, but the observer is rotating away from the sun, which we are in that model. But how far are we going? The Earth is rotating at about 1,675 kilometers an hour, 1675. Depends on where you are though, it's faster toward the equator. Now to make the math work, we would need to convert those kilometers to miles. This would be about 1,041 miles per hour. It's pretty fast. It's fast as shit. Now from 12 p.m. to 6 p.m., approximately when the sun sets, you would go 6 times 1041 miles, or about 6,246 miles, not accounting for the curvature though. Just to make the math simple, that's about how far you would go. So that's a long way, right? Explains the light refraction, changing color, mirage? And I don't think so. Not at all, actually. You need to consider the relative distance that you are rotating away from the sun, out of the whole distance. The sun is 93 million miles away from the Earth. Relatively, we are not moving far away from the sun at all in this time period from 12 to 6. In fact, we moved 6,246 miles away from the sun out of the total 93 million. So doing the math, the distance we traveled divided by the total distance is 0.0006716, or 0.0672% rounded. So objects look distorted and refracted as they get further away. Good, I get that. But you're trying to tell me that an increase or decrease in distance that light travels of a measly 0.062% is going to cause the sun from looking white in a perfect sphere to dark orange, rippling, and misshapen? On the flat Earth model, these calculations are not exact, but the sun could easily go from the estimated 3,000 miles above your head at noon to 5,000 miles away from you at sunset, which is almost double the distance out of the total distance. That's almost a 50% increase, about 744 times that of 0.0672. This much larger increase or decrease in distance could much more easily explain the phenomenon of light refraction regarding the sun and the distortedness and change in color.
Mind you, the sheer presence of a pressure gradient at all causes problems for flat Earth, but that's a whole different topic. Now, a few people have actually made the claim, incidentally, in previous videos, that the moon does actually change in angular size, appearing larger at the horizon. This is actually false, though. This is, in fact, an optical illusion that's often referred to as the moon illusion, whereby our brains are tricked into thinking that the moon looks bigger when it's near the horizon, but in reality, if you measure its angular size when it's near the horizon, either by photographing it or even just holding up a coin at arm's length that almost covers the moon, and then repeat it later when the moon is high in the sky, it's still the same angular size.
And it even shows the beautiful little moon getting smaller as it goes away from us.
Interestingly, there have actually been studies done on the idea of using the globe itself as an atmospheric lens, because curved atmosphere bends light around it. So if you parked a telescope in space where the light was converging and looked towards Earth, then the light that it can see being refracted by the atmosphere would be giving a magnified view of the universe. Anyway.
Wow! The land of make-believe!
Just space exploration period, if we're getting these images from Hubble and Sophia, which is a 747 special purpose, with the same exact technical specifications when it comes to the telescope, Sophia's taking the same exact pictures of Hubble. And that's where the disparity in image analysis comes in, because I have a half a dozen photos I took off of NASA's website for Hubble and Sophia, and when I ran them through MATLAB's image processing toolbox for comparative analysis, those images came from the same source, and it wasn't at 330 miles above the surface of the Earth. So that's
Anyway.